So welcome everyone. Today we're going to talk a little bit about the multi-region capabilities that exist in CockroachDB. But before we do that, let's talk a little bit about Cockroach Labs as a company. For those of you who may not be familiar with what we do, Cockroach Labs was founded by 3 ex-Google employees in 2015 with a mission to create the world's greatest distributed relational database management system. And we've been growing pretty rapidly on the people side since then. This photo on the right was taken during our last in-person holiday party in 2019. And since then, we've close to tripled our total numbers. Even since February, when I delivered our last meetup, we've grown from 200 people to more than 350. And we're also evolving as a company as well. And earlier this year, we raised our Series E round of funding. Of course, as many of you probably know, we're also the creators of CockroachDB, our open source database offering, which is also available as CockroachDB Serverless, a free forever cloud offering that scales as you grow. CockroachDB Serverless entered beta today, so it's hot off the presses. So you might want to check it out if you're looking for a database to build your next world-changing application off of. Since some of you I know are local to the city of Toronto, and that's where I and Bilal work as well, I thought I'd spend a minute talking about how our presence in the city has been evolving over the past few years. We first opened a small office in the city in mid-2019 with 2 Waterloo grads, and that's substantially grown, and we're taking in more than 10 local interns every year now. The team in Toronto is focused on engineering, and we have a very well-rounded team which has representation from all areas of our engineering organization, from engineering efficiency to database internals, and even to our managed cloud service like CockroachDB Serverless, which we just talked about. We also recently just signed a lease on our new office at 33 Yonge Street in downtown Toronto. We're pretty excited about that space, and we hope to be in it by the end of the year. We've also more than doubled our team here in Toronto in 2021, and we hope to do the same in 2022. So if you're interested in learning more about the Toronto office or just about working at Cockroach Labs in general, stick around after the talk, and Bilal and I and Michelle and Debonair will stick around for any of your questions. Okay, so with that out of the way, let's talk a little bit about CockroachDB before we get into the talk about multi-region databases. If you're not familiar with CockroachDB, you may be asking yourself, seriously, another database? Yeah, it's true that there are a lot of different database vendors out there, and we're yet another one. So what's so special about CockroachDB? While we've had relational databases for 4+ decades now, and we're in our 2nd decade of NoSQL databases, cloud-native distributed SQL databases are still in their relative infancy. What CockroachDB brings to the table is the ability to scale easily and broadly, as we'll discuss shortly, do that with extreme high availability guarantees, support strongly consistent transactions, and do so for next generation cloud-native applications, which require all of the above, but also the ability to scale from 0. While there are database systems out there that handle some of these attributes, we feel that there are none that could match the complete value proposition that CockroachDB brings to the distributed SQL transactional market. To make all this possible, CockroachDB is built on a novel distributed consensus-based architecture that allows it to operate across geographical borders and also across cloud service providers. It's quite impressive how easy the system is to scale. All you need to do is spin up a new CockroachDB node, point it at the rest of your running cluster, and you're done. The system does the remaining hard work to move the data around, to balance the load, and the whole time ensuring transactional consistency. That's CockroachDB at a high level. There's tons of resources online if you want to dig more into the internals and how it works. But today we came here to discuss the technical details behind multi-region databases and applications. So let's get started on that. First, let's start by trying to understand why people would want a multi-region database. So back in the olden days, databases ran on big machines, typically the biggest machine a company could afford. And generally there was only one of them. So although that database ran very fast, if the machine had any problems, the database was offline. And this was obviously bad, since even though machines back then were surprisingly more fault tolerant than they are now, they did occasionally go down. So to address this problem, databases were re-architected to run in clusters of nodes. So here you can see a standard configuration of 3 nodes running in parallel. And in this configuration, if just one of your nodes burst into flames, the rest of them would continue to service your precious database workload. Even so, when this technology was first invented, while it was a huge leap forward from what existed in the past, it was still very expensive, as you now replace your one very, very expensive machine with 3 very expensive machines. But then 15 years ago, AWS changed the equation. Obviously, with the benefit of hindsight, it's easy to agree with Andy Jassy here. EC2 has been a game changer for our entire industry. Now, nearly anyone can set up a database on a cluster of nodes and get high availability without breaking the bank. In fact, earlier today, I spun up a 100-node database cluster, used it for a few hours, and then deleted it. This is something that was unimaginable only 2 decades ago. But even with all this computing power and flexibility, there were still a couple of problems. First of all, most database software 2 decades ago wasn't designed to run on a large number of machines. Secondly, those that were designed to run on a large number of machines typically had to have their nodes close together geographically, generally within a few hundred kilometers. Here's some documentation excerpts from 2 of the earliest distributed transactional systems, both of which exist today and are still widely used. As you can see here, they clearly state that the distance between the nodes can negatively impact performance, and the best practices are to keep the nodes less than 50 kilometers apart. Now, this may seem like a decent distance for availability because it's pretty rare for an event to take out a 50-kilometer area. That being said, every once in a while, something like this happens. This is a satellite photo of the infamous 2003 Northeast blackout. And as you can see by this huge black spot here, on the East Coast, that's several hundred kilometers that got knocked out, some of it for more than 24 hours. Having your database nodes all concentrated in one geographical location can be good for internode latency, but it leaves you exposed to widespread outages like this. And it's not just power outages you need to worry about, but also hurricanes and earthquakes, and even more mundane things like internet traffic routing issues. Imagine if this outage from 2003 reoccurred today, but only a few hundred miles further south. That would take out AWS's US East 1 region, which is easily the most critical piece of public cloud infrastructure in existence today. If you had all of your database nodes concentrated in that single region, you'd be out of business. No problem, you say. I know how to solve this. Instead of having database nodes in a single region, you'll place them throughout the globe. Then, if US East 1 goes down, no worries. You've got US West 1 and SA East 1 and AF South 1 and others. Your database is almost guaranteed to be safe from widespread region failures. Aside from requiring a complete re-architecture of most transactional database systems, this would be a truly great idea, provided you never heard of these guys. Of course, the man on the left is Albert Einstein, the father of relativity, and he taught us that while time is relative, the speed of light, unfortunately, is a constant. The guy on the right, if you don't know who he is, hold tight. We'll talk about him in just a bit. So first, let's talk the speed of light. So how fast is the speed of light? Objectively, the speed of light is ludicrously fast, over 1 billion kilometers per hour. So with speeds that fast, what's the problem? Well, the problem is that the speed of light is too slow. So you may be asking, how could 1 billion kilometers per hour be too slow? Well, let's have a look at how this maps to cloud network latency. So this is a heat map that shows the interlatency round trip time between regions in Google Cloud. And this is courtesy of Big Bitbus. As you can see, the darker colors are fast and the lighter colors are slow. So I'll give everyone like a couple of seconds to digest this plot. But there's the main point that I'm trying to call out here is that there are many inter-region round trips which are well into the 200 and 300 millisecond range. And you can see them up here in the lighter colors in these areas over here. This is still pretty fast from a human perspective. Most humans can't perceive changes that are less than 200 milliseconds, but many database customers need their transactions to resolve much, much faster than that. We see customers fairly regularly that need sub 50 millisecond transaction resolution. And there's even some that need sub 5 millisecond resolution. Clearly, with those tight requirements, spreading your database nodes across the globe isn't going to be feasible. No worries, you say, I'll keep my data geo-distributed, but I won't perform a cross-geo round trip as part of my transaction. Or maybe you'll run the transaction and then you'll perform this cross-region communication asynchronously after the transaction commits. Well, that brings us back to this guy. By now, some of you who didn't know his face immediately may have figured out that this is Eric Brewer. For those of you who don't know Eric, he's a UC Berkeley professor and a Google employee. But what he's most famously known for is he's the father of the CAP theorem. I'm not going to do the CAP theorem much justice today. So if you don't know about it, I'd encourage you to read up about it in your own time. But the gist of it, at least as it applies to this conversation, is that if you want consistent transactions, you need to do that round trip before you commit your transactions. Well, to be more precise, if you want to be able to support strongly consistent read-write transactions on the same data from every node in your database cluster, you need at least one synchronous round trip to occur during that transaction commit. Even if you do that, however, you may soon realize that unless you're very careful, you may need to perform multiple round trips to commit some distributed transactions, especially if you're using a chatty protocol like two-phase or three-phase commit. It's for this very reason that we've spent considerable effort in CockroachDB optimizing our commit protocol to ensure that whenever possible, we only perform a single round trip at transaction commit time. If you're interested in reading more about how we've done this, you can search on Google for parallel commits. And the first link that comes up is our blog post about the work that we've done in this area. Anyway, we're a bit off track here, but I wanted to give you a sense for the fact that there are a lot of parts of the system that need to be optimized to ensure that multi-region transactions are fast. With that being said, let's get back on track by taking a step back. So why do people want multi-region databases? We already talked about why you might want a multi-region database for the availability properties and the complications that that entails. But while we haven't bottomed out on how we solve the issues around performance when you're trying to achieve these availability properties on a widely distributed database, I promise we'll get there. So just bear with me for one more second. So what's the other reason why people want multi-region databases? As it turns out, the answer is low latency. It may seem a bit paradoxical, especially because we know that the speed of light is a limiter to low latency in multi-region databases, but multi-region databases can actually help lower latency in a very specific way. So let's walk through an example which should hopefully make this all a little bit more clear. So imagine you built the new hottest hiking app, say to take on the likes of Strava. And you start with a small user base in the Northeast United States, but then as user adoption explodes, you've now got users all over the world. The problem is when you designed your app, you only set up a database in a single region, US East 1. And as a result, whenever your users need to access their data, they need to issue queries, or worse, they need to write data against your US database, regardless of where they are in the world. Going back to this heat map, some users are going to experience 300 plus millisecond delays, which is going to make your amazing new application seem sluggish to 90% of the world's population. So how do you solve that problem? The solution to the problem is to place database nodes as close as possible to where your users are. If you do this carefully, you can guarantee that your users will always be less than 50 milliseconds away from a database node, as your app can always connect to the node that it's closest to. But you're probably asking, what about these guys? Yeah, I haven't forgotten about them. They make things difficult, but not impossible. Let me try to explain. So to understand the power of multi-region databases, it's important to understand the common access patterns of multi-region data. And really, there's three of them. In conducting extensive amount of customer research, we found that these are the three common access patterns that users are looking to optimize in multi-region settings. The first and most common one is the one we just discussed. You have user data for a bunch of users that are spread out throughout the world, and you want them to be able to access their data fast within their home region, the region where they created the data and the region where it's most commonly accessed. The second use case is where customers want fast access to data everywhere in the world, but that data is mostly read-only. In other words, it's rarely updated. So you can think of this as reference data, and we'll talk about an example of this coming up. Finally, there's some data that will only be accessed in a single region. So customers want ways to ensure that a given table is always fast from a single region. Earlier this year in our 21.1 release, we made multi-region super simple for CockroachDB users by creating table localities for each of these common patterns. And you can think of these as shortcuts to achieve advanced multi-region behavior. If we go back to the hiking app for a moment, you can imagine a table of user hikes, which record where each hike took place and all of the stats about that hike. You'd imagine that we want this data to be quickly written and accessed in the region where the hike occurred at the expense of slower accesses in other regions of that data. For that, we've created what we call regional by row tables, which ensure that individual rows stay fast from within the region where the data was created. We may also want a leaderboard in our hiking app, say of the most prolific hikers across the app. This data is likely to be read a lot by every user every time they open the app, but changes very infrequently. For that, we've created a global table, which prioritizes global read performance over write performance in any region. And finally, you can imagine that we might want a historical and statistics table, which stores data aggregated in ways that would be useful for the data scientists in your company. Since those data scientists all work in a single region, say US East 1, it may be beneficial to have that data optimized for read and write access in that single region. That's all great for users, but since we've got what I have to imagine is a mostly technical crowd here, I'm guessing some of you are wondering how these tables work under the covers. So let's have a look at that. Under the covers, regional by row tables are partitioned by region. The table has a hidden region column, which is used as a partitioning key. And the system is configured to pin each region's partition to the set of nodes residing in that region. This will make all reads from and writes to a given region's partition fast within that region. In this illustration, you can see each partition is represented with a different color. And you can see that we also keep replicas for each partition of data in the specified region, so that we can provide high availability of that data should there be a disruption to one of the nodes in that region. Obviously, due to time constraints, I'm glossing over a bunch of details here and enhancements we've built into the system to ensure that queries don't slip out of a region unless strictly required. But this is the high-level story. What I personally find coolest about regional by row tables is that all of this magic happens under the covers, and the user only has to issue this one DDL statement shown up above to set it all up. Underneath the covers, the system does the rest. With global tables, we replicate all data to all locations. That solves the fast read problem, but how do we manage writes to all of these replicas? More specifically, how do we prevent writes from impacting reads on the table? What we do to prevent the impact is that we assign writes to some point in time in the near future. This prevents present time reads from seeing them and waiting on them to commit. Then when it comes time to commit the write, we wait out the gap between future time that we wrote it at and the present time to make that write visible. Now, if you're very confused because this all sounds pretty complicated and futuristic, rest assured, there's an example coming up. But in addition to the complication and the confusing aspect, it's also a pretty elegant way of ensuring that reads are always fast in these global tables. So to explain how this works in a bit more detail, let's walk through an example. So here's a more detailed look at global tables in action. There's a lot going on in this slide, but I'm going to try to walk through it all. So don't be put off by the complexity at first. When we start writing over here at the leader's replica, which is this replica here, we're at time 9, but we're going to write this row at time 12. So this row is only going to appear in the database at time 12. But then we start replicating, and we need to replicate to all of these other replicas to ensure that they know about this before we can commit the write at time 12. So we start replicating, and in doing so, we have to confirm that there are no reads in progress at time greater than 12. Now, what's nice about this approach is that reads at time 12 aren't possible yet, because we're only at time 9, and then time 10, and then time 11. Meanwhile, while we're writing, the reads are occurring here at time 9 and here at time 11 without waiting, because they're not blocked on any of the work that we're doing at time 12. So our replication requests make it through to all of the nodes, and then they make it all the way back to the leader and arrive back at time 11.8. Since this write doesn't technically occur, excuse me, doesn't technically occur in the database until time 12, we need to wait out this time difference between when we arrive back and time 12. But then once we get to time 12, we can commit the write and return transaction success, and the whole time ensure that no reads have waited on this write. So hopefully this seems more simple than as I presented it at first. It's still a little bit complicated, but I also think it's pretty elegant and a pretty neat way of solving this problem of making global writes non-blocking in a widespread database. If you're interested in more details as to how these global tables work, we have a blog post in the works that will get into even more detail. Okay, finally, we have regional tables, and regional tables ensure that all reads and writes are fast from a single region, in this case, US East 1. Here you can see that the US East region contains all of the table's replicas, and this means that reads and writes are going to be fast from that region and slower from the other regions in the cluster, because they have to interact with US East to read or write data. To make the impact of remote access a bit less severe, we also maintain what are called non-voting replicas in remote regions. So when writes occur in the US East region, the data is replicated to the local replicas, which are the voting replicas. And once a quorum is reached, the write can be committed. But then in the background, we replicate data to the non-voting replicas asynchronously. And this ensures that we're never impacting transactional latency to replicate the data to the remote regions. Now, having non-voting replicas in remote regions allows us to service consistent but stale reads in those regions without having to incur the network latency of traveling to the table's home region. It's important to note that we can only service stale reads in those remote regions, because the region may not contain the most recently committed data, since it's only being replicated asynchronously. These stale reads are triggered in CockroachDB using this as of system time syntax in queries. And while I didn't note it earlier, we also maintain non-voting replicas on regional by row tables, so that stale consistent queries can run on each partition's data, regardless of the region you're in. So that covers how we improve latency with multi-region databases, but what about availability? Recall that we still want to be able to handle situations like this. But the problem is that in all of the table locality examples I showed, all of the replicas are kept local to a given region, except for the non-voting replicas, which can't service consistent current reads anyway. So for example, there was this. So what gives if all of the data is local to a region? Doesn't that mean that we're back to the same old availability problems? In this case, if US East 1 goes down, all of the data in our stats table will be unavailable. And placing non-voting replicas doesn't help either, as we can't use the non-voters to service consistent reads or even write to them. So to solve this problem, CockroachDB allows configurable survivability. If you want to be able to survive a region failure, we offer that flexibility, but you need to be aware that it comes at a cost. So let me first explain how we achieve region survivability, and then hopefully it'll become pretty obvious why it comes at a cost. So if we want to ensure region survivability with a quorum consensus algorithm, we know that we're going to have to ensure that we don't have a quorum of replicas in any region. Keeping a quorum of replicas in a single region means that if that region goes down, the given replica is unavailable for writes and consistent reads, since we've lost a quorum of the replicas. So to solve that problem, we place a quorum of replicas outside of that region, in this case, using the neighboring regions. So with this setup, we know that if any of these regions, any single one of these regions fail, the other two regions can carry on unaffected, since we'll still have 2 of the 3 replicas available. And this is configurable at the database level with the single command shown above, alter database survive region failure. It's important to note, however, that there are performance implications to this configuration. Before we were able to achieve our quorum of replication on writes in just the home region, but now we need to get at least one other region involved, which requires a cross-region round trip. In actuality, we don't just move the replicas around. If you set the database to survive region failure, we'll also allocate additional replicas, up to 5 in total. We'll store 2 of them in the home region, as you can see here, and the remaining 3 will be spread out over the neighboring regions. This not only provides for additional resiliency, because we can now survive the failure of 2 replicas instead of just 1, but it also ensures that if we lose 1 replica in the home region, we have a second available replica to act as the leader in that region, the one we want to be fast. And this ensures that in the single node failure scenarios, we can still service fast reads from the home region. And writes continue to require the same number of regions to participate in quorum, since we can achieve quorum by accessing only 1 additional region. In cases where you lose 1 replica in US East 1, we can still achieve quorum by participating with this US West 1 region. Okay, if there are more available regions in the cluster, we'll continue to place non-voters in each region where we don't have a voter, so that will maintain fast, stale access from all regions. And of course, if your objective is performance and not region survivability, the best bet is to still keep all of the voting replicas in a single region, so that write operations don't require a hop to a remote region. We call this zone survivability, and it's the default for newly created databases. Providing survivability flexibility is key for multi-region databases, as customers will have different requirements. Some will want local performance at all costs, while others will need to be able to handle a region failure. So where does that leave us? While it's true that multi-region databases present a lot of complex problems, there are also ways to get around them. Multi-region databases have come a long way in the past few years, and if you're looking for improved global latency and survivability, it may be worth giving them another look. And of course, there's much more to be done. While I've hit on the high points of multi-region databases, there's obviously a lot that I've left unsaid, like how to place data to ensure that domiciling requirements like GDPR are met, which regions to place replicas in when running in region survivability, and others. We've solved some of these problems, but others are still a work in progress. So if any of these problems interest you, we're always looking for talented and curious people to join our team. Also, if you want to learn more about anything I've spoken about today, or